in the first 4 series of our videos, we have seen how to solve the first order differential equations, what are the different types of it, and we saw like 4 methods of solving them, which were like separation of variables, linear method, the integrating factor, and we saw the exact equations, how to solve them, and we also saw the matrix method. We also looked at the real values and the complex eigenvalues in the last series of videos, and we have concluded the first order differential equations with that. Now we are going to extend our analysis to second order differential equations, and we'll see how to solve them and what's common, what's not common, and everything else. The second order differential equation is usually of the general form y double prime being a function of y, y prime, and t. This is something which you already know, right? So because if it was y prime, then we'll just have y and t. So if we have a second derivative, there's a good chance that we might also involve a first derivative term in the equation which we have. When we are going to extend our analysis to second order differential equations, we still can't solve through one initial condition, right? Because in the first order differential equations, this one initial condition was enough, but over here, that's not possible over here. We need 2 initial conditions, which is something different from what we had last time. And the general forms of the 2 initial conditions can be something like y at t naught, or time t is equal to 0 is y naught, and y prime at t naught would be y1. This is just some general, a very general form of initial conditions. It need not be this ones, but yeah, we'll just say that these are the common ones. With this, a second order linear differential equation would look something like y double prime plus p of t times y prime plus q of t times y is a function that is g of t. Again, this is something very similar. We're just adding one extra term to a first order linear differential equation. And again, as usual, if g of t is 0, it would make it homogeneous. And if it was non-zero, then it's non-homogeneous. This is again something which is the same from the previous ones. Using this knowledge, we're going to look at different cases, and over here we'll be primarily looking at the real life examples. The very first video which I've done on differential equations, I said that we'll be giving a primary focus in dynamics. So we'll be looking at the mass spring system over here, and however we are also going to look at, okay, so this is going to be a primary focus, but we are also going to focus on pendulums, simple pendulums, and also a little bit of circuits. In the next video, I'll be giving you the general equations that govern these equations.